Now I'm just introducing what is research that those doing. She's in the experimental research group work on kinetic activity of enzymes in the bodies, and there are large and huge, but the active site is quite small. It is little active site typical activity with transition metal, or very small organic molecule can be transformed against thermodynamic favor. So catalysts make barriers lower. And here, well, of course, it is her project and she can redecide, but it was another student 2 years ago starting the things. So there is a hydroxyl from solvent coming to this iron inside the porphyrin, or this NO molecule is laughing gas, something that if you have local anesthesia, you can inhale and feel like after a cup of beer. So this OH attacks here, creates nitrous acid and then departs. So this is imported from a student who was doing similar project in the computational chemistry, which I invite everyone to take in the spring if you have availability of limits in your thing. And the interatomic distances and energies are imported from this ab initio data, and then it reconstructs the potential as function of this distance between laughing gas and attacking OH, and then the laughing gas and iron. So originally this distance contracts, and then upon collision it overcomes activation barrier and departs. And since it is a quantum class as a main focus, here are the two-dimensional wave packet dynamics, where this reaction is happening on a quantum language, where several paths can happen simultaneously. So y-axis is laughing gas to OH, x-axis is iron to laughing gas, and if one, well, not one, if Sibel pursues the simulation long enough, the two-dimensional distribution wave packet will move towards the product. So there is a chance that there will be two two-dimensional projects this year, one by Joe and another by Sibel, and the rest of us probably will do one dimension, which is still very, very cool. This is interesting, but a little bit challenging computationally. So the CPU will run the fan and may run overnight to get these things. So last time in the lab we went over how to model a single atom in one dimension, right? So you recognize this this equation. If one puts several atoms together, it will be like lattice, mimicking oligomer, polymer, or solid. And this is motivation for the project by Sibel. Like if there is a interface between organic dye and solid semiconductor, upon photoexcitation, electron transfers, and then it closes the circuit and gives electric current. So the potential for this setup should look approximately this way. So lattice and a little well for a molecule. Here are the observables that we did cover in the last lab, but they were not covered in your presentations. So if one is speaking about some completion of some reaction, then it's very typical to chop the space on regions corresponding to reactant and product, and then integrate until this midpoint, and from midpoint to the end, and then probability here and there will be probability of reactant and product. They should give 1 if you add them together, and if one monitors this probability as time passes by, they may go regularly with some like quadratic or linear, and then one can take slope as a reaction rate, or they may show some crazy behavior which then one needs to explain by words. But if the behavior is regular, if one can extract the slope, it is a big deal, and easily gives a chance to analyze results, like changing initial conditions, extract slope, and then analyze the slope as a function of initial conditions. And Adam will decide what is his initial condition, either temperature or offset of the parabolas. Sometimes, yes, it looks irregular, and then one needs to do some tricks. So it's both Adam and Lola who will be doing this project. So if you need to just finish the course, parameters are not as important. But if you are thinking about mimicking realistic life and making connection between what you do and research, there are key parameters which needs to be either obtained by educated guess from literature or extracted from first principles through helpers. So what are parameters for Adam and for Lola? Their projects do have 2 potential energy surfaces, quadratic, but these potential energy surfaces are for different electronic states. Therefore, they may have different energy, right? Their offset energy, and they may have different equilibrium position, which means upon change of electronic state, bond expands or contracts, right? And the value, how much equilibrium position changes, is a parameter that will drastically affect all outcomes. The energy offset is a key parameter that will change. And another, so typically what is available experimentally is to, and what can be converted into like slopes and offsets, is energy of this minimum, and then 2 additional points. How tall is the second parabola for the equilibrium coordinate of the first one, this point, and then how tall is the first parameter at the parabola at the equilibrium of the second. So if these 4 points are known, the rest is basic math. Adam, do you support? Did you hear about this parameterization of Marcus model, or what it is something new? Yes. Can although we are short in time, but maybe you can just briefly share what you, maybe in 1 minute, what about parameterization of Marcus model? What do you remember from your inorganic class?
I honestly don't think so.
But do you recognize the picture?
Yes.
And what, based on your inorganic class, what did control the intersection point? Because this height of the intersection point controls the activation for transition.
I think it was just the different energy states, like specifically the different ground state energies.
So it is not enough. You may inspect your slides, your materials from your other class, and look how you see if you go along blue and then go to red, there is a little upwards and then downwards. And this little change higher up in energy is activation, which needs to be overcome by temperature. And based on the equilibrium and offset and curvatures of the parabola, there is a simple, relatively simple algebra to express the heights of this activation barrier. And it is not avoidable. You will need to do it anyway for this project, for this class, and you better refresh memories and about this thing. Okay.
Does it have anything to do with the inverse Marcos, where if you keep shifting the
yes
of the product,
blue goes up. Let me. I'm showing something with fingers, but it's not focused here. So just a quick. Going to center and in. So if we move blue parabola up or red parabola down, right?
Yeah.
Then the intersection will move into the minimum of the top parabola, right?
Yeah, and that
it will be activation less.
Activation energy of the transition state.
Activation energy will be 0 for this activation less regime. And if you keep moving blue parabola up, it will be crazy thing. It will be barrier going to the blue intersection will be to the right side. You need to go up to the crossing point and then down. And it is called Marcos inverted regime. Yes.
Yeah. Okay.
Yeah. Thank you for the question. I'm happy to observe you aware of this details. So a little bit. On how Lola and Adam will go forward with their calculation, how their version of the code is working. And I understand that it's so we are spending time instead of academic material, but this part will be included at least in the last academic lecture. So I'm just giving a little bit ahead of time. And I believe it is something interesting and useful. It's more fun than rotations. So in each of the parabolas, we, as you saw in the last lab, there are independent wave functions, right? On one hand, like blue and red or whatever we call them. But at the same time, it is a one molecular system. They are connected to each other. So for this situation, our wave function is combined as two column vectors, just written together in a one super column vector. So first we list everything related to ground, then we list everything related to excited. If the size of the number of grid points is n, then for this two potential energy surfaces problem, the size of the wave function will be 2n, n for one, n for another. And then the Hamiltonian, which was for n grid points, it was a matrix n by n, right? As Wyatt did introduce to us, right? You were showing. So if we double the size of the wave function, then size of Hamiltonian also will be 4 times, like 2n by 2n will be 4n squared. And if we write it as a matrix, we can separate it on blocks. So the top left block will affect only the ground state wave function, and it will be absolutely identical to what we had before, kinetic plus potential for ground state, right? If you look for lower right, it will affect the excited, and the Hamiltonian will include kinetic plus potential energy surface for excited state. Then we have two additional blocks which are responsible for mixture, for transfer of probability between these potential energy surfaces, for actual transitions between these two electronic states. And in this current version of the codes, it will be just unity matrix multiplied by the value of coupling. And in more advanced theory, it is something that comes from so-called non-adiabatic coupling that at least Lola recognizes what it is, right? Lola?
Yes.
Okay, yeah, thank you. And if someone wants to be really, really meticulous, which goes above the requirements for this class, but it will be used as a little foundation for computational chemistry. So the wave function of this system is consisting of both electronic wave function and nuclear wave function. They need to be set up as product. But since there are more than one potential energy surfaces, we have two products. So ground state electronic function times vibrational function for the ground state, plus excited state electronic function times vibrational wave function for excited state. And if we want to look for transfer rates in this setup, then reactant and product are integrated in the same way, but we are not looking for the center of the cell. We're looking for all components that correspond to ground, and we call it like reactant product, and we look for all components of the excited and call it reactant, or if I am confused what to call reactant and product, I can call them just left and right. Make sense? Okay. 20 minutes for the lecture. Did you ever saw the figure displayed on the slides? Do you recognize does anything clicks, or it is absolutely new? We saw it, we never saw it, maybe something, but I don't remember what it is. Adam? No, you should ask either yes or indefinite. It was a part of CHEM2.
Oh,
I will tell it to you, CHEM2 instructor. So what do you think about? What is your idea? What it may mean? Which system it may correspond to?
this is a man. Is this bond energy stuff? Is this
No.
vibrational?
There is vibration, and is there anything else?
I can't read.
But you can open it on your slide if it is not.
Oh, yes.
So here. So which molecule it is for?
Hydrogen chloride.
So which motions hydrogen chloride? What hydrogen chloride can show us?
Well, motions.
Yes.
Stretching.
What else?
And I guess vibration.
So vibration of the stretching, and is it always oriented along z-axis, or it can change its orientation in space?
Oh, it can. I mean, Yeah, I can flip and rotate. And
Okay, yeah, good enough. Yeah, thank you. I think it is a good start to help. Anyone else wants to comment on it? Or you better listen to what I will try to say. Okay, so HCl molecule is not nailed to a space. If just HCl is hydrochloric, it can evaporate from liquid phase. It will be toxic, but it does exist, right? You can infuse one HCl into a box of vacuum, and then if you do not have electric magnetic field, gravitation will not make it orient. It may be randomly distributed at any angle, right? And if we slightly kick it, it may convert kinetic energy of a kick into rotations, right? So typically, to make a molecule to rotate takes much lesser energy than to make it to oscillate. So it's still motions of ions, but it is much less energetic motion because center of mass is not moving, and the rotations can be approximately described intuitively with classical language, but experiments show that rotational motion is also quantized. So there are certain preferred speeds or frequencies of rotations which can be taken by molecule, and intermediate values are not acceptable. Make sense? So there is an experiment which on one hand manifests this property, on the other hand, it serves as a signature of simple molecules, like primarily diatomics. So because quantization of rotations strongly depend on their masses, and even if you change mass slightly, like isotope in the HCl, one can there are typically chlorine is in the 50-50 mixture of isotopes, right? And they will give different signatures. So if you have only one molecule, you can, by doing rotational spectroscopy, you can tell which one is there. Or if you do enrichment of isotopes, it's one of the way to select it. So this lower panel shows so-called rotational vibrational spectrum. So it happens response of a molecule to electromagnetic radiation of the infrared frequency. So if we consider oscillations of H and Cl bond, we already accept, based on our previous chapter, that there will be potential surface and there will be quantized states, right? Ground state and excited. And their offset is substantially smaller than any electronic excitations, but it is quite big. It is like infrared of, I wouldn't say it from the top of the head, but something like 0.2 electron volts, like small, not small, a fraction of electron volt. Maybe a tenth of the visible yellow quantum, so something substantial. But if one would try to agitate this molecule with infrared light, which is approximately tuned to the transition from ground to excited vibrational, one would see that transitions, like you have a beam of infrared light and then you have a detector. So at some frequencies, it will pass through to detector, at some it will be absorbed by a molecule. And you'll see that this absorption happens only at specific wavelengths, specific frequencies. So it appears from understanding that ground vibrational and excited vibrational have sub-levels. So it can be no oscillations, ground state of this oscillation, but at the same time, it can rotate quicker or slower, right? And this energy, depending on how quick or slow it rotates, will be a little higher or lower. Same for first excited vibration. There is a subset of levels. And then if one does analysis of so-called selection rules, which show probability of transition, and it deals with matrix element of position operator. If you do selection rules, one can find that transitions, optical transitions, are available only between selected pairs of this vibrational and rotational states, and vibrational and rotational states here. So not every transition is available, and not every energy is possible. So only selected pairs of states are available, and the states differ from the central, from the frequency when it is absolutely equal to excitation energy of the vibration by little offsets, both to the increase and decrease of energy. And the shape of the intensities of these transitions also looks like wings of an eagle. So intensity increases, then decreases, increases, then decreases. And a goal of the next chapter, one of the goals of the next chapter is to get an idea about these transitional energies. And the goal of PChem2 is to explain about their intensities. I will give a brief comment, but it is basically not the area of this course, because it will deal with occupation, probability, partition function, and chances to predict the spectrum. Does it go enough as a motivation? The second motivation is to learn more about rotations of electron in the hydrogen atom, which like before we were discussing it with Bohr model, and now we want to use more advanced theory. Okay, this is something we should be able to discuss at the end of this chapter, or maybe in the middle of the PChem2 course. No, this is too much. We need a lot of material to understand this figure. I have no idea how dare I put it here. Since I'm showing, there is a little heads up. If you look on vibrational energies, their offset will increase, and the degeneracy, like for oscillations, each energy corresponded to one state. For vibrations, there will be degeneracy. The higher the energy, the more states of the same energy. And it will be also kind of a new concept. And if one dumps all input information into formula for spectrum, one gets this wings. Okay. So slowly but surely we go to actual material. So the goal of the next chapter is rotational motion. If we pose this goal, we need to set up tools that can help us to describe it and to derive some equations to quantify rotational motion, preferably on quantum language. So when we were speaking about translational motion, like in one dimension, our main door to the quantum world was quantum operator of momentum, right? Which is derivative of over position. And as soon as we accepted this concept, we were able to do wonders. and you keep doing them in the projects, or you will soon. If we are going to rotational motion, it goes on a curve. So linear operators derived for linear motion are not as helpful, and we need something new. It is possible to make analogy and describe rotational motion with only momentum, like momentum along x and y in the plane, and it is very similar to what Joe will show in his project, but it is much heavier, and it is available for numerical solution. But if you want to write pen and paper, it is a dead end. One needs to find shorthand and elegant notations where everything will be simple and short. So we need to quantify circular motion with some applicable, useful operators and variables, and then we need also to quantify energy, like kinetic energy for rotational motion. So the things that we are going to use, and I hope to derive within remaining whatever 7 minutes, are the operator of angular momentum, which will look very similar. We will try to establish analogy with linear momentum and curvilinear momentum. But here, one would need to take at least derivative over the arc length. If you already know the trajectory, we need to make derivative along the trajectory. And if we want to establish an analog of kinetic energy, we can look on our standard operator of kinetic energy in the following way. If you multiply, so it is p squared over 2 mass, right? So if you multiply numerator and denominator by distance, by r squared, then it will be rp squared divided by mass radius squared. It's a little trick, but I'm just giving heads up. We will see it soon. And this trick will help to make an elegant expression for kinetic energy. Okay. Simplest rotation is on a circle, although we know that it's not always true. Planets go on elliptical orbits, right? You know it, not circular, but circular is a good start. So radius from it could be either like HCl molecule, or it can be electron revolving around nuclei, and we can set up radius, angle to parameterize this rotational motion, and then radius times angle will be arc length, right? So radius times arc length, or if it is a very small change of angle, it will be a small change of arc length. So from here, we immediately see that the ratio between angle and arc length is 1 over r. Later on, we will use it. So I want to point your attention to this little symbol. We can do in the same way as later on we will learn from Joe, to have x and y and define wave function everywhere, right? But one can say that we do have only fixed radius, and then we want to explore wave function along this circle. And we may want to establish connection between these two approaches, these two visions. So there is a way to transform function, to parameterize function, not as x and y Cartesian projections, but as so-called polar coordinates. polar coordinates, okay? And they also define this two-dimensional space. So distance from center and angle. And if we want to establish a derivative over arc length, we do the, how do you call it? Not chain rule, but derivative of the complicated function. When it depends on these two variables, but we want a derivative over the other variable. Is there a fancy name for this trick, for this approach in calculus? Change variable. Okay, I believe you. So if we need to take derivative over L, arc length, we can do it first derivative over radius, and then derivative of radius over arc length. So canceling dr will give this deep psi over dl, so it's possible. And since there is a second variable, we do the same trick, derivative over angle, and then derivative of angle over the length. So if for a couple of lectures we assume that radius is not changing, that we are just staying on circular trajectory, then this delta r is 0, and we cancel this term. We have only the second. And then this derivative over arc length will be equal to the second term. So derivative of psi over angle, and then derivative of angle over length is always constant. It's 1 over r, right? So we are doing very little first step into differential geometry when one goes on the non-Cartesian coordinates. And there are ways to transfer derivatives from one system of coordinates to another one. Okay, so if we want to make an analog of momentum, but momentum along the arc length, we are no, we will not do it. We will use the concept of so-called angular momentum, which stays constant if a particle moves on a circular or elliptical trajectory, but the higher angular momentum, the quicker angular motion, right? So it is in 3-dimensional, it is cross product. In 2 dimensions, it just radius times momentum along this arc length. And if we plug in the definition of analog of momentum along arc length from the previous slide, so 1 over r, derivative of angle, and here we have radius from definition of angular momentum. Make sense? Then we cancel distance, and we get the Planck constant imaginary unit and a derivative over angle. So this will be quantum operator of angular momentum. We can call it LZ if our motion is happening in X and Y plane, because in 3 dimensions, it's always perpendicular to plane of rotation. And this will be our main building block to describe quantum rotations. We will find its eigenvalues of its square. It will enter the Hamiltonian, and we will make an analogy to everything we did before for other things. I think time is over, and we will continue on Friday from this point. And I look forward to see you tonight in the lab. Okay, meeting is done. Everyone is welcome to disconnect. I'll stay here to answer questions if any.
Right.